All right. So today we're going to talk about NMR. This does require a little bit of maybe physics, recalling physics. So what happens here is if you think of the nucleus, there's my sphere, so you can see it in 3 dimensions. A nucleus, we say, has a spin. And why did it? Now it's moving my arrow. Okay, so we can kind of think of it on an axis, and it's spinning on that axis. Um, well, the nucleus is a plus charge. What we do know from physics is what happens when we have current. And I think I've mentioned this to you before, maybe it's the other class. What happens when we have current moving in a circle, in a loop? It creates a magnetic field. And you can turn your fingers in the direction of the current, and your thumb points in the direction of the magnetic field. Right? Well, I might have mentioned that in terms of the benzene ring causing pi-pi stacking, which threw off the RS in our TLC, in a different lab. But here now we're talking about the positive charge of a nucleus going around in a circle. But just because it's a positive charge rather than negative electrons going around doesn't mean it doesn't produce a magnetic field. So in the theory of quantum mechanics, we figured out that one of those variables, one of the variables in that equation is these things have a spin associated with them. Normally, you've talked about it with, if you remember your, I forget the name of the person. When you're filling orbitals, right, you had to have spin up and spin down. So you've probably talked about spin with electrons. And that was to represent that your plus 1/2 and your minus 1/2. Plus 1/2 is spin up, minus 1/2 spin down of the electron. So you remember that filling rule for filling orbitals in what you probably learned up to this point about quantum mechanics. They have a spin. They will generate a magnetic field of sorts, different energy of that magnetic field than the nucleus. Okay, so the premise behind NMR is to measure that magnetic field of a nucleus spinning. So in essence, the NMR is measuring all the little magnets in a molecule. All the little magnets, okay? You can probably begin to imagine that a spinning nuclei is going to depend a lot on its environment. It's going to depend a lot on the electrons that are around it, what it's bound to, how many bonds it has, things along those lines, and different types of nuclei. So different types of nuclei, whether I'm looking at a carbon or a bromine or a nitrogen, that's going to give me a different magnet. And so we're really talking here about what we call magnetic moments. So it's going to have a little bit different magnetic moment, and how can we measure that energy? Well, just measuring a magnet may not be the easiest thing, but anytime you have something in quantum mechanics that's in one state, spinning, what prevents this from being tilted on the axis and spinning like that? In this case, I'm going to have a magnetic moment in one direction. In this case, I'm going to have a magnetic moment in a different direction. So there's really no constriction on how the nuclei spins and on which axis it spins. There's nothing that orientates it, nothing that locks it in one particular spinning type of motion. And it can move around on that too. All right. So all these little magnets are pointing in a bunch of different directions. Each direction kind of is a different state. So to like de-randomize this, align them all. My mom, to amuse us when we were younger in church, had these little dogs with magnets on them, and you put them on a piece of paper and you could kind of move them around and make them do things. You ever seen that?
Yeah.
And then if you put the dogs orientated in the wrong direction, like they're supposed to go head to tail, but what happened if you put them tail to tail? They spin around and go, yes, okay, you know what's going to happen here, right? So the application of a magnetic field, north-south pole kind of magnetic field, relative to a bunch of little magnets, all these little magnets are going to want to do like the little dog magnets, and they're going to want to line up with that magnetic field. This is bigger, stronger, and so when that's applied, all the things that were once random all the little magnets then align with that large magnetic field. But what if there's one that gets out of place? In fact, what we can do is we can get them all to line up, and then we hit it with energy, and that energy causes the things that are all lined up with the magnetic field to kind of get out of alignment. So now they're in an excited state. Oops. Magnets, get my letters in the right order. So in a higher energy state, what we call an excited state, just like when we have electrons, right? If we had electrons, we put them in an excited state, they relax back down, and they would give off light. You could see through the little spectrum, you could see all the little bands of light from those Balmer series of energy states for an electron. If you remember that wonderful lab from 211 where you had to peer through the little thing and look at all the little, yeah, okay. And everybody seemed really happy about it too. Most fun you ever had in lab. Well, at the same time, when we do spectrophotometry, I should say absorbance, if you did use the spectrophotometer, something that has color, a little bit different, maybe it doesn't even have visible color, but it absorbs in the UV range of light. What happens there is it's absorbing that light and putting electrons in an excited state. And so you can measure the absorbance of that wavelength of light. Okay? Just so happens the energy to put things in an excited spin state, put my magnets out of alignment of the field and into an excited state, then that lies in the radio wave range. Not visible light, not UV, Last week, we talked about things that landed in the infrared range of the electromagnetic spectrum. I even briefly, maybe said too much about X-ray crystallography at Argonne National Laboratory. We even talked about electromagnetic radiation in the X-ray range. I think you guys were the ones too that asked me about if they were all the same. What's the difference of enantiomers? And that we talked about the polarized light. I happen to notice one of the labs over here has a polarimeter. So now I have to figure out how to use that. It's old where you have to kind of peer through a thing and get a lamp, I'm assuming, and figure out somehow to measure an angle. I don't know, but we definitely have some chirally pure samples that we could put in there and measure that rotation. So I got to think about how to get that incorporated into the lab curriculum now. We have it, let's use it, right? This one though is radio wave. Now, radio wave is not real high energy electromagnetic radiation at all. So you put things in a huge magnetic field, give them a radio wave that pulses them, puts them in an excited state, and then as they relax back down, they give off a radio wave. And we can measure radio waves, right? It's like tuning into a radio station kind of thing. Okay, nobody does that anymore. It's like using your cell phone, I guess. Those are all radio waves, right? So you'll have to keep in mind, we now have better instruments. It used to be in the day where things weren't shielded very well, and that if the campus had a radio station that was beaming out radio waves to be used, it would interfere with your NMR. Now, those are the days before cell phones. I can only imagine what a cell phone might do to measuring those radio waves now. All right. So we're getting, and I'm not even telling you what radio wave we're getting. I don't know what station it is. I don't know what the hertz are off the top of my head. That depends on which nuclei and what's around that nuclei as to the exact signal. But I can measure exact signal. I can scan through all of my stations. If I scan through all my stations and I get a signal, I create a peak. And we can see those peaks, and that's what we're going to observe in an NMR. Now, that is the basic premise here. Okay, it's the basic premise of an NMR. It's also the same technology that's ever used in an MRI. I don't know if any of you have had to have an MRI yet. I've not had to have one, but what do you know about the MRI? They put you first in a big magnet, right? They got to put you in a big magnet. So what you probably didn't realize and didn't necessarily sense in that process is when they put you in that big magnet, all your nuclei inside of you were lighting up with that magnetic field, and then they're pulsing you with radio waves and waiting for those to relax back down. It gives off signals based on the environment it's in. Now, that's a lot of signal. And so they're not seeing peaks, but they can see intensity in certain ranges, which give off then translated into color, image, three-dimensional, I don't know, but I don't know exactly how that technology works, but it's the same basic idea of large magnetic field, pulse that thing, measure the radio waves, and the intensity of that radio wave in certain frequencies, they're able to generate an image from that without necessarily seeing particular atoms. All right. And in fact, with MRI, I'm not even sure. We do take our machines and we tend to tune them. And tuning them has to do with what nuclei we're looking at. We generally don't look at all the nuclei simultaneously. We don't look at the whole, it would take us way too long. We're not looking at everything. We're just kind of looking at a narrow range. All right, like FM versus AM, I guess, something like that kind of idea. Yeah.
Theoretically.
Yeah.
If I take a little magnet and I go like this, I could like align my nuclei.
I mean, people do wear magnets for whatever, and it's supposed to be healthy and healing, right? Haven't you seen that? Some athletes, they have it on the bracelets and stuff like that. You haven't seen that? Julie knows what I'm talking about, right?
You working?
Yeah, back right now. Yeah. Next time you're gonna come into the test, you're all gonna be having, they look like headphones, but they're really magnets. Because if you align all your nuclei somehow, then your brain waves would be better or something like that. Now, I don't know. People make up all kinds of stuff. Right now,
Magnet shower. You can have
I don't know, but there's people that feel like it alleviates pain or swelling or something. I don't know.
My grandpa.
Really? Yeah. Well, I mean, there's people right now. This is off topic, but there's people right now. It's all what peptide therapy.
Wasn't they
And no, peptide therapy. I mean, I even saw a billboard going into Fort Wayne last night for peptide therapy, and I'm like, a good portion of the population hears peptides and ooh, that's new. And then all of us who had a little bit of science would be like, protein? What? You're gonna put protein therapy? I mean, I am protein. I eat protein on a regular basis.
You are.
What do you mean peptide therapy? Right? What were you saying?
What?
It's one of the things I start out with is muscles is protein, right?
Yeah.
That's all peptide, and you would have no structure really. Well, bones, but I mean, you really need muscle for shape and function. So yeah, or even for that matter, how does your cell have a shape at all?
It
What's
has
that?
the internal membrane.
No,
No, it has the
no, it's not the membrane. That would be a bacteria.
Cytoskeleton.
What?
The cytoskeleton was
I've never heard it called cytoskeleton. So one of the ways that we treat cancer now, that's like how paclitaxel works. That's bacteria again. So bacteria has shape because it's under high osmotic pressure. And the cell wall just gives it strength to hold that high osmotic pressure. What's that? I can't believe you haven't been taught this. Oh my gosh.
the stuff on the inside wants to.
So one of the first things I worked on at Bristol Myers Squibb was antibiotics. So this was near and dear to my heart. Okay, so osmosis, right, is when you have
Osmosis Jones.
Again, peptide therapy. Osmosis is when you have two solutions of different concentration it'll flow through an otherwise impermeable membrane and try to balance out the concentration on either side of that membrane. I didn't realize this, but when I started teaching nursing chemistry, they need to know osmolarity, because osmolarity, you better have the right concentration, osmolarity in an IV bag.
It also goes boom.
What does it do to your cells? If you're hypertonic, if you add a solution into your blood that's hypertonic, what's going to happen to a cell?
It's going to explode.
No, opposite.
It's going to not explode.
Right? Because it's more concentrated, more concentrated outside the cell than inside the cell. So water's going to want to flow out of the cell into the outside and shrink the cell. Whereas if I went with a hypotonic solution, it's less concentrated, wants to flow in. That can cause a cell to burst unless you have a cell wall. Most of our eukaryotic cells do not have a cell wall. What are the two types of cells? I know. But anyways, two types of cells that have a cell wall.
Plants and bacteria.
Yeah, there you go. Plants and bacteria. That's why a plant, when it's dry weather, wilts because it loses that osmotic pressure and it loses structure. Bacteria, again, high osmotic pressure. The way we kill most bacteria with like penicillin, cephalosporin type antibiotics is it interferes in the cell wall biosynthesis, weakening the cell wall, And it doesn't take much of a pinprick in a cell wall that once it's weakened, it bursts.
So theoretically, I can make plants explode.
I don't know if that's the same cell wall.
No.
Would a antibiotic, like a penicillin-based antibiotic, actually interfere with the cell wall biosynthesis of a plant? I don't know that answer. I've never tried. Not with me. I don't have much interest in killing, well, maybe weeds, but so anyways, I heard a guy give a talk, and he would give a picture of the bacteria and then the bacteria on drugs. So the bacteria, he literally had a picture of the bacteria exploding. It was awesome. I mean, that was formative in my education to see bacteria explode. All right, so high osmotic pressure in a cell wall. Yeah, so that's why bacteria, that gives them shape. What I was getting at, protein wise, microtubules. Microtubules in the cell are that you might call it the cytoskeleton. I'm not sure, but we always called it microtubules because your paclitaxel and related types of anti-cancer agents interfere in microtubule production. So they can't do the stretching meiosis, mitosis, whatever stuff. I can't keep those two straight. I'm not a biologist. Right. So people don't want to take peptides, but peptides give us structure. Peptides have all kinds of function. But, to the regular population, peptide sounds like, ooh, that sounds technical. That must be great, right? It's how we advertise things. It's how we suck people in. Back to NMR. All right. So taking NMR, and feel free to put a magnet all over your body. I don't know that it's going to do you much damage. That's one of the things about an MRI, right? You can probably have more than one MRI in a year, whereas more than one CT scan, they get a little bit more nervous about that. They're hitting you with higher energy. You're bombarded with radio waves all the time. That's not as big of a deal. All right. But you don't go into the MRI with money in your pockets, coins in your pockets, keys. My sister, when she went to get her first MRI, apparently had metal in her shoes. So that in the MRI, all of a sudden her feet went right together. So, yeah. I hope that you find that connection between what we're doing with NMR and MRI. Here's where it completely deviates, though. We're not going to get pretty pictures of molecules. You're going to get a spectrum with a bunch of peaks on it. What do those peaks mean, right? How are we interpreting those peaks? So, going through this basic idea that we have an excited state and a ground state. Once we have it in that large external field, and that difference in energy state lands in the radio wave frequency. All right. Oh, give me that back. Okay, there we go. Some things that make our radio wave frequency different. Shielding. I'll get there eventually. Which nuclei? All right. And I don't understand all this, but they almost have some multiple of the spin 1/2. When the spin becomes 1, it no longer becomes NMR active. It doesn't somehow. I don't know all the math behind that, but they have to have a spin of 1/2. So examples: hydrogen, and we have to look at specific isotopes. So hydrogen 1, not deuterium, not tritium. By the way, deuterium, pretty weak, which is why we put deuterium in our NMR solvent, because it won't show up in our proton NMR. carbon 13. What's the most abundant isotope of carbon? 12. And it's about 99.4 or 5% carbon 12 naturally.
Yeah.
So when I go to take an NMR and look at carbon, I am trying to look at roughly 0.5% of all the carbon that's in there. So relative to the hydrogen, where this is 99.9% 8 hydrogen, this is very abundant, and that signal will always be very strong, whereas carbon 13 is a much weaker signal simply because there's less of it available. You can't kind of just like make your body all carbon 13. Right? Your body's going to be mostly carbon 12. So then, you have a probability of getting an NMR signal of 0.5 to 99.5. Those odds aren't great. So that's why you get a much weaker signal on a carbon 13. I think nitrogen's a really tough one because it's nitrogen 15. Nitrogen 14, again, doesn't show up, but nitrogen 15 does. And so we don't see a lot of people doing nitrogen NMR. I don't know of anybody doing an oxygen NMR. So oxygen 16 is not a spin 1/2. So you will not see oxygen. In my life, fluorine. Fluorine 19 is really abundant again. So fluorine NMR is a really obvious spectrum. Phosphorus, and I am trying to remember off the top of my head. I want to say, is it 31?
Yeah.
Okay. Sounds about right. I was going to say 35, but yeah, you're right. I'm thinking chlorine there. Yeah, 31. You're right. P31. Now, again, that's one of the more abundant isotopes of phosphorus. So phosphorus will show up in an NMR very abundantly as well. So these are some of the more common ones. This one tends to be tough, very tough, very tough. Most of the time it's hydrogen and carbon. Carbon tends to be very weak. Yes?
But none of those show up on the NMR?
No, these are the ones that do show up. These are the ones you can observe in the NMR.
So the NMR is pretty limited.
You'll see. Stick with me. It's limited in which atoms it can observe. Now, here's the point of this is it is quite difficult to observe these nuclei simultaneously because these spins, these little magnets, all lie in a much different frequency. So we have to have different receivers. Essentially, we have to have a different receiver to detect those different signals. There are some now that are broadband, and some of the best broadband probes can measure proton, carbon, fluorine, and phosphorus, not nitrogen. And again, I've not seen anybody try to do oxygen or much beyond that. When in a good broadband probe, then you might be able to kind of, it's what we call two-dimensional NMR, and you can kind of measure those like two nuclei simultaneously, but that's getting really advanced to begin to describe, well, we're pulsing in one frequency and observing in another, and so on and so forth, and how that affects the two spectra. But anyways, for the most part, you observe one nuclei at a time. Your machine's tuned in to pretty much one frequency at a time. That's how you run it. That's how you set it up. You got to tell the machine to do that. It's looking at one nuclei at a time for the most part. That is not to say the magnetic field from a carbon could affect the magnetic field for the hydrogen, and more likely vice versa. Or this is a crazy one. If you have a fluorine in your NMR or a phosphorus in your molecule, the presence of the fluorine and the presence of the phosphorus will affect the signal, that the radio wave of that proton, of the hydrogen. So we observe one thing at a time, but neighboring magnetic fields start to affect the magnetic field I'm trying to observe. That's the important part here for you to understand. One of our little elements as we go on. All right. For us, we're going to mostly look at proton. Carbon's a lot harder to look at, much weaker. It's really not as informative. I don't learn as much from the carbon as I do from the proton. Having said that, the ACS standardized test likes to throw on carbon spectra that really doesn't help you much. You can probably get the structure. Most molecules on that test you could solve with just the proton NMR. You probably cannot solve it with just the carbon. I would never try to identify anything from just a carbon NMR. Now, if I had carbon and a proton, sometimes the two together can be helpful, more often in the two-dimensional side of things than in the one-dimensional side of things. But that's graduate level. We've got a limited amount of time in 311 to try to cover this, so we're going to focus on proton. And everything we learn with a proton can be applied to other things in carbon and phosphorus and fluorine, just slightly different numbers, all right? So right now we're going to focus on just hydrogen NMR and look at just hydrogen NMR. Okay. So there are three elements that happen here. Different nuclei can affect my radio wave frequency. Different neighboring different nuclei. So a carbon could affect a proton. But in any one organic structure, there's how many hydrogens? A lot. If all those different hydrogens are different, right? They're all kind of spinning differently, creating different little magnets. The neighboring magnetic field of another hydrogen can affect the hydrogen I'm trying to observe. All right? So first thing is, and the second thing is, electrons. Electrons will affect my NMR. Now, for the most part, electrons essentially absorb some of that magnetic field. Okay? So for the most part here, I want you to think of it as absorbing that applied large magnetic field. The slight caveat to this, slight extension of this, is that the stronger the magnetic field that I apply, the larger the difference in the two excited and ground states. So that tends to give better resolution. We don't get confusion as to which state it is because but that's going to be a larger difference, a larger energy, and therefore a different frequency. So a larger magnetic field creates a different frequency. In a relative sense, it's still the same, but I applied a larger magnetic field and got a larger radio wave from it. So when we use bigger magnets, we get better resolution in our NMR. It's sort of like going to high definition from low definition screen kind of thing is really what it does. Everything will look sharper, clearer in a high magnetic field. The one we have here, 90 megahertz. That's how we measure the strength of our magnetic field. It's a 90 megahertz machine. First one I think I ever remember using was 60. Spent the summer at Wheaton College, and they were excited because they had just gotten a 200 megahertz NMR. Quite an upgrade from 90. Well, in those days, it wasn't as bad, but to get to those higher magnetic fields, they are superconducting magnets. To get superconducting, in other words, you get very little resistance in your materials that you're putting electricity in to create that magnetic field. You have to super cool it. It has to be very, very cold. The colder the material gets, the less resistivity there is in the material, and with certain materials, for sure. So I think this is where niobium is part of the magnet, and they supercool that thing, and then they charge it, and it literally rests on a bed of liquid helium. Liquid helium has a really, really low temperature, so it's super, super cold. Now liquid helium has become very, very expensive, and it's really difficult, very expensive to maintain one of these magnets because you have to keep it on liquid helium. If it loses the liquid helium, it says quench. You quench the magnet. You can recharge a magnet, but boy, that's really expensive to get back in there, supercool it again, and recharge that magnet, regenerate that magnet. So you never wanted it to get quenched. Well, liquid helium, harder to come by, and all that kind of stuff. So what they did is they insulated. There's another layer on the outside of it full of liquid nitrogen. Liquid nitrogen's enough to keep your liquid helium cold enough that your liquid helium would last longer. So in a typical machine, every month you had to refill with liquid nitrogen. About twice a year, every 6 months, you had to refill with liquid helium. Now liquid helium's become really expensive, and that can take a big chunk, like tens of thousands of dollars out of a budget for just one magnet. So that was 200 megahertz. And then, I think by the time I got to the University of Michigan, we were routinely working on a 300 megahertz NMR and maybe a 400 megahertz NMR. But boy, when you really had a good thing, then you went to the 500 megahertz. By the time I got to Vanderbilt, they had for biological applications, I think at that time was up around 900 megahertz, almost to a gigahertz. But we could, they brought in a 600 megahertz NMR, and there the antenna that measures all your radio waves, that got super cooled. That was superconducting, so it was even more sensitive, and I could use less material to get my NMR. That was really awesome too. And then carbon became much easier to get carbon on that really sensitive probe. If I went to Vanderbilt now, I think they have a 900 megahertz for general use, and they're up to like a 1.5 or 6 gigahertz. Like the biological takes up like 2 more floors. It's just massive. I cannot imagine how much liquid helium they go through there to keep that stuff alive. But that's the problem with superconducting, and we don't have superconducting here. But boy, by the time you get to that really large, really strong magnetic field, boy, your resolution looks really sharp. And if you supercool superconducting electronics in it, boy, you could even get a better signal from something that would otherwise be fairly weak. I don't think any of the MRIs require or rely on superconducting magnets that I know of. They're all permanent magnets, which means you've got to get a really big footprint. Those MRI machines take up some space, right? Yeah. Except you get no spaces from what I've heard. It's very cramped inside of an MRI. I've never been in one, but I heard it's very cramped. I won't even get into the whole thing about spinning the sample and why that's important and all that kind of great stuff. So in an MRI, you don't get spun, thankfully. The magnets spin around you. In our machine, the sample gets spun and the magnet remains static. But here's the important part of looking at now how these neighboring magnets affect signal, radio wave, and how electron spin affects my radio wave. All right? All theory, all background, none of that really helps you interpret a spectra, which is what we're going to ask you to do. So let's get into the nuts and bolts now of how this now affects my spectra that I want to be able to analyze. This is recording just fine thus far. I can't tell if it's inverting my words on the screen. I gotta keep an eye on that, make sure it doesn't get chopped off again. So I'm gonna tell you to this way. And I want you to approach every NMR spectrum this way. First, chemical shift. Second, integration. And I'm going to tell you preemptively, there's a large portion of spectras can be easily determined from just the chemical shift and the integration. I say that because most of you are going to fear the third one the most, and that is called splitting. Okay? Let's now look at each of these separately. Chemical shift is that effect from the electrons. All right? So chemical shift literally is kind of saying, what is the frequency of a nuclei? The exact frequency. I can't even tell you how many decimal places, but the exact frequency of the nuclei that I'm looking at. Okay? So here, again, we're tuned in. We're really only looking at hydrogens. So I'm looking at a molecule. I'm looking at a hydrogen on that molecule. It will have a peak that shows up at a particular frequency. And it's literally, it's not like IR where it's broad, it's all over the place. It's not like IR where you're seeing a lot of peaks that land in the same region or anything like that. These will be relatively unique. So where it lies is its frequency, and the largest effect on its frequency is the magnetic field that it fields. The magnetic field that any nuclei is feeling is going to be dependent on the electrons around it. Okay? It's going to be dependent on the electrons around it. Another way of saying this, technically all hydrogens would have the same radio wave. Not all hydrogens are experiencing the same magnetic field, and the frequency, that difference between relaxed and excited state, ground state and excited state, the difference between that is determined by the magnetic field. So if I applied a uniform 90 megahertz magnetic field, if all hydrogens were the same, they'd all have the identical frequency. But because they're experiencing, based on the number of electrons around them, a different magnetic field, they end up having a different difference between ground and excited state, a different chemical shift. So we're going to look at a spectrum for hydrogen, roughly 0 ppm to 20 ppm, but more often than not, we'll cut that off at about 10 because we really don't see a lot of useful protons. Most of the time, we don't see useful protons below 10. What's a ppm? It's an interview, and somebody asked me, "Oh, so is ppm you're talking about in NMR?" It was a non-chemist. ppm and NMR, is that like the same as concentration? And I'm like, I'm not talking about concentration. I know ppm concentration of a solution, but I'm like, I don't think so. The organic chemist who came with me after, it is. And I'm like, well, now I know that because when we report certain things from the NMR, we have to do it in hertz. Hertz is the frequency of the radio wave. So the observed hertz, that's your signal, divided by the magnetic field. You guys remember what I told you we have here? What's that?
Is it
90 what?
90
Megahertz. A mega is what? 10 to the 3rd would be kilo.
Mega's 10 to the
10 to the 6th, or not negative, but 10 to the 6th. So a megahertz is 10 to the 6th hertz. I'm taking hertz divided by 10 to the 6th hertz. What do I get from that? 10 to the minus 6.
Yeah.
What do you do in ppm?
Oh.
Multiply by a million. 10 to the minus 6 multiplied by a million. Boom. It's 1. So this is why all of our chemical shift is reported in ppm, which is really the hertz divided by the megahertz. What happens, I was alluding to this now, but what happens if my magnetic field jumps to 200 megahertz? So at 90 megahertz, let's say we observe something at, I don't even know what the, let's say 10, sure, I'm going to say 10 hertz. 10 hertz, I observe the signal at 10 hertz in a 90 megahertz NMR. What do I end up getting here? Sorry, I got that backwards, don't I? I should say, let's say it was 900 hertz. 900 hertz on a 90 megahertz machine. What do I end up with for ppm? 10. 900 divided by 90. 10 times 10 to the 6, you take it off, it's going to be 10 ppm. Perfect. What happens if this magnetic field becomes now a 200 megahertz NMR, but I'm still looking for that same peak, that same nuclei?
It moves up.
Now it's not observed at 900, but it's observed at 2000. So now I got 2000 divided by 200, still giving me 10 ppm. So even though I go to a bigger magnetic field, I'm getting a different hertz for that signal, but when it's divided by the magnetic field, it still gives me the same ppm. That's the clever part about it. So your chemical shift ppm should be the same no matter how big your magnet is. We can take an NMR here and we can match it to literature, right, Kate? We can match it. This is what we have to do for research, match it to literature, and it matches what somebody else might have done on a 400 or a 500 or a 600. To publish, we have to go and ship them off somewhere else to get them run on a 400 megahertz NMR. We can't publish with a 90 megahertz just because the resolution isn't real good. It's much fuzzier. It's fuzzy. Okay? Integration. But what if in an organic molecule you've got a lot of hydrogens and they're essentially in the same I don't know, same number of electrons are around them. Now what? They're all going to be the same. So integration is going to reflect a symmetry. Integration is going to reflect symmetry. So all the protons that have the same radio frequency wave signal. Where is Victor? He's still not here. He's probably sitting over by the lab. I don't know. We tried to look for him. I tried to look for him. I thought he would have thought to come over here. We'll have a break here in a little bit before we start analyzing, looking at actual spectra. Okay. So it tells me how many protons have the same signal. So, and then integration is literally integration. It is relative. It is the area under the peak. And this is going to be true. You can't really integrate some of the other spectra. You can certainly integrate a proton spectrum, but it's all relative. And what you're going to find out is the more hydrogens there are, bigger the peak. Kind of makes sense, right? I've got more signal at that frequency because I have more hydrogens with that same signal. So we can get chemical shift, we can get integration, I can find a peak, look at that peak, where it's at on the spectrum, like, ooh, it must be around this many electrons. And, oh, there's at least 3 or 4 or 5 of them all in that same basic, around the same number of electrons, right? Splitting. So it's not the same as absorbing the external magnetic field, but my ability to spin this magnet is affected by a neighboring magnet and it's spinning in its magnet. That's affecting its magnetic field, and therefore to go from excited to relaxed is affected by that other magnetic field sum. So it's not a pronounced effect, it's a much smaller, tinier difference that it's causing. All right? Now, I want to be clear. Most of the splitting we're going to look at is due to another hydrogen that's not the same, because if it was the same and have the same frequency, if they're all the same, they all kind of come together. It's a hydrogen that has to be different. If there's a hydrogen that's different next to it, that will cause splitting in my peak. What was normally one peak is now more than one peak. All right? You can get splitting from a carbon. The problem is, if I'm looking at a hydrogen that's 99% abundant, and I'm looking for a carbon-13, is the only one I can observe, looking for a carbon-13 that's 0.5% abundant, that's a, 99 to 1, less than 99 to 1 ratio. The only time you might see that splitting is when your signal is very strong, usually when your sample is very concentrated, and we call them spinning sidebands. You'll notice them because they're about equal distance, about 1 to 99 in intensity next to that peak you're looking at. So sometimes you can see that. It's very, very rare. Don't look. Do not look for carbon causing a splitting in a hydrogen. On the flip side, if I was in a carbon spectra trying to observe my carbon nuclei that's 0.5% abundant, every hydrogen on there will affect a splitting in that carbon. And that creates very complicated signals in the carbon NMR. So I never see anything but what we call a decoupled carbon spectra. In other words, there's a way of putting in radio frequencies and pulsing things so that the splitting caused by the hydrogens gets erased over time. And all you see in carbon spectra are single peaks for single carbons. That's it. Okay? In hydrogen, proton NMR, we're going to see some splitting depending on what's around it, how many hydrogens are around it. I'm not going to give you any molecules of the fluorine or phosphorus in it, but this has happened to me, that if I have a phosphorus or a fluorine in my NMR spectra, those are abundant enough and strong enough signal, they will cause splitting of a hydrogen that I'm observing, in addition to the splitting caused by a neighboring hydrogen. So there are times when a fluorine or a phosphorus in your molecule could cause the splitting. Again, for you guys, that's not going to be very often. For you, all splitting will be coming from neighboring hydrogens. Okay? So now, with those three things in mind, chemical shift, integration, and splitting, when we look at any one molecule, we can look at that NMR spectra, and from the chemical shift, from the integration, and from the splitting, we can start to piece things together to determine the structure of my organic molecule. It is not the same as X-ray. I am not looking at the exact spectra. However, by deduction, you're going to be able to say, oh, I have these kinds of hydrogens, and they're next to these kinds of hydrogens. Therefore, I'm going to put them on the next carbon over and start to build the molecule together. And you can really solve some very complex spectra. When you get a lot of carbons, a lot of hydrogens, cyclic structures, things like that, it does get a lot hairier, and we're going to avoid that. But that's when we start to rely on what we call our two-dimensional NMR, where I'm looking at hydrogen relative to carbon, one bond away, 2 bonds away, hydrogen relative to hydrogen, and one of the other one's favorites, it's called NOE, and that is, it's not a hydrogen next door, but it's a hydrogen that's way over here, but because maybe conformationally they came close through space, that causes an effect, so you can kind of use that NOE effect. That's really what's behind it. We solve protein structure by NMR. So a really large molecule, I can find the hydrogens on an alanine side chain of alanine getting close to a phenylalanine over there, and because of that, I have to have an alpha helix in between inside. And so you can kind of, that's way oversimplified, but you can use NMR to determine the structure of a protein. But you need a 1.5 megahertz, gigahertz, sorry, instrument to do stuff like that too. Sometimes they use the N15 coupled to hydrogen, and that helps them as well too. But very, very complicated. Let's take a little, brain wash. That's not the right word. Brain cleansing. There we go. Let's try that one instead. Moment of about 5 minutes here, and maybe we'll find Victor. If you need bathroom, sip of coffee, I don't know, whatever. Come back here 5 minutes, and we'll start looking at that packet of NMR spectra and how to interpret those peaks using chemical shift integration and splitting. So it's better if I just kind of walk you through it, show you what it looks like, and then go from there. If we have time, hopefully I have time, at the end of this, we're going to go into the lab, and I have a bunch of samples that all they have on them in a molecular formula, and you can take an IR and an NMR of that sample, get you that experience, and then eventually what will happen for your grade for this portion of it is I'm going to have you analyze all those spectra, all those IR, all those NMR, to determine what the structures are. So I have one for each of you, 13 different molecules. That's a lot. So I got to give you some time to work on that one. But that's also the final exam of this class. The final exam of this class is you'll be given a similar sort of situation, unknown spectra. You've got to go run, analyze, determine the outcome, and that's your final test. I think it's good to do it now, and you have some practice before you do that for a final. And I can help you work with you now, but the final is kind of like you just got to do it. So, all right, 5 minute break. Let's say come back at what 10:45. 10:45, we'll get started again.